Fertilizers are very important to improve the quantity and quality of the crops. Half of the protein required to feed the world's population comes from the plant sources. Plants need nitrogen to produce protein. Ammonia is the only viable source to produce nitrogen, which helps in the formation of protein. And this ammonia comes from the fertilizers. Ammonia is a very important fertilizer. 85% of the ammonia produced industrially is used in making fertilizers. So the main use of ammonia is in fertilizers like urea, ammonium sulfate, etc. So it is very important for improving the quantity and quality of the crops. So let's see how we can prepare this ammonia in laboratory and at an industrial scale. So in laboratory, we use this reaction, that is, we use an ammonium salt, we use ammonium chloride, and we make it react with calcium hydroxide. So it forms CaCl2, that is the corresponding salt. It forms water and it releases ammonia gas. Ammonia is a pungent smelling gas. In this case, when a salt reacts with a base, it forms another salt and another base. But in this case, the other base formed is NH4OH. And this is very unstable. It readily decomposes to give H2O and ammonia. So whenever we heat an ammonium salt with an alkali or a base, that is calcium hydroxide, we get the corresponding salt, water, and it forms ammonia gas. This is the reaction that we use in laboratory to prepare ammonia gas. This is the experimental setup. We use ammonium chloride and calcium hydroxide. It is heated. It forms the vapors of ammonia gas, which also contain water vapor. Therefore, it is made to pass through calcium oxide. This layer of calcium oxide absorbs all the moisture, so we get dry ammonia gas, which is collected in another test tube. Let's see how it takes place. So when we heat the reagents, ammonia gas is released. The water vapor is absorbed by calcium oxide. It forms dry ammonia gas, which is collected in an inverted test tube. Ammonia is lighter than air, so it displaces the air, and by the downward displacement of air, since it is lighter than air, it can downward displace the air, and so it is collected in an inverted test tube. So this is how we collect ammonia in the laboratory. Ammonia is lighter than air, so it is collected by downward displacement of air. Air is heavy. It can be removed or displaced by the lighter ammonia gas. We have to take one precaution in this case. As you observed in the experimental setup, the beaker or the flask is kept in a tilted position. This is because in the reaction, water is being formed. So to avoid the coming back or the trickling of water back in the flask, which can lead to an explosion, we take or we tilt the flask so that the water formed does not trickle back into the flask. So we keep this precaution in mind during the laboratory preparation of ammonia. Another way to prepare ammonia is by using the nitrides. In this case, magnesium nitride reacts with water to form the corresponding hydroxide, that is magnesium hydroxide, and ammonia gas is released. Similarly, any other metallic nitride, aluminium nitride, reacts with water to form the corresponding hydroxide, and ammonia gas is released. But we do not use this method in the laboratory because this is expensive. Though it forms ammonia gas, we prefer the first method over this method, as this method is slightly more expensive than the first method. Complete the reaction. We have a metallic nitride and it reacts with water. So the nitrides react with water to form the corresponding hydroxides and ammonia gas. So now let's balance it. So whenever the metallic nitrides, they react with water, they form the corresponding hydroxides and release ammonia gas. Now, let's prepare aqueous ammonia. Ammonia is highly soluble in water. So let's see what is happening in this case. We take the same reagents, that is ammonium chloride and calcium hydroxide. They are heated, they release ammonia gas. Now this ammonia gas is highly soluble in water. Observe what happens. So as the ammonia formed is highly soluble in water, if we take a very narrow test tube to dissolve it in water, since the test tube is very narrow, at one time all the ammonia cannot be dissolved as the rate of dissolution is very high. The ammonia comes back into the flask and that leads to the breakage of the flask. What happened? In the first case, we were taking a very narrow test tube or a very narrow glass tube to dissolve the ammonia in water in order to prepare aqueous ammonia. Since we are taking a very narrow tube, the rate of dissolution is so high that at one time it cannot dissolve all the ammonia. Since the rate of production of ammonia is very high, as the dissolution process is slow, most of the ammonia is sucked back into the flask and that leads to the breakage of flask. That is, to avoid the back suction, we use a funnel arrangement. In this case, we have to increase the surface area so that the amount of ammonia which can be dissolved is more. So what do? Instead of taking a very narrow glass tube, we take a funnel. This increases the surface area. Now, more amount of ammonia can be dissolved. So observe what happens. So now in this case, we get ammonia gas. We are using a funnel arrangement. So as ammonia gas is produced, it is dissolved. Some water rises in the funnel, creates some space in between. As more ammonia gas is produced, it pushes the water back and it falls. Now let me explain again what is happening in this process. In this process, we take a funnel arrangement. So first of all, water is taken in a trough and a small portion of the funnel is dipped in water. We are taking a funnel arrangement to increase the surface area of the ammonia that can be dissolved. So we immerse some part of the funnel in water. Next, ammonia dissolves in water at a higher rate than which it is produced. Now in this case, the rate at which it is produced and dissolved is both high. But since the solubility of ammonia is very high in water, so it gets dissolved at a very high rate. So now, since it is getting dissolved at a very high rate, what happens? The pressure inside the funnel above water decreases. This is because as the ammonia is produced, it is dissolved in water. So it creates a partial vacuum or a partial low pressure. Now what happens? The pressure in the funnel above water decreases. So here above the funnel, there is low pressure. Inside the water trough, there is high pressure. So to equalize the pressure, water from the trough rises into the funnel. Now as this water rises, the level in the trough that decreases. So the level inside the trough that decreases. So this creates a loss in contact. Since the level of water in the trough that falls, so there is a partial or momentary time in which the funnel loses its contact with water. Now, more of ammonia is produced, it pushes the water back into the trough, and so the funnel is again dipped in water. So in this case, we avoid the back suction by using a funnel which has a higher surface area. As ammonia is produced, it gets dissolved. Now a partial vacuum or low pressure is created. So to equalize the pressure, water from the trough rises into the funnel. Now as more ammonia is produced, it pushes down the water, and so this process continues till the water is saturated with ammonia. So now in this process, by using a funnel arrangement, we can prevent back suction of ammonia. And this process continues till the water becomes saturated with ammonia. So we get aqueous ammonia. Now what is this aqueous ammonia? This means ammonia reacts with water. We know when ammonia reacts with water, it forms ammonium hydroxide. But this ammonium hydroxide is highly unstable. It dissociates back to give ammonia and water. So when we talk of aqueous ammonia, it's actually ammonia in the liquid state. Since ammonium hydroxide is highly unstable, it gives back ammonia and water. So aqueous ammonia is actually ammonia in the liquid state. Now let's look at the industrial method of preparation of ammonia. Right now we saw how we prepare ammonia in the laboratory. Let's look at the industrial method of preparation, which is known as Haber process. So the two gases, that is nitrogen and hydrogen, are made to come in contact with one another using a catalyst, iron or molybdenum. The reactants are heated to a high temperature. So they form ammonia gas. This is what happens at the industrial level, where there are big plants to manufacture ammonia. So this is how the process is taking place. We have nitrogen and hydrogen molecules. Now they are compressed. They are compressed to a very high extent. As they are compressed, the atoms separate out. So the hydrogen and nitrogen atoms, they separate out. Then they are passed in a catalytic converter. In this catalytic converter, we use iron or molybdenum. This only increases the rate of the reaction. So we have the nitrogen and hydrogen atoms. They combine to form the ammonia molecule. So as you see, ammonia is being formed. Then this ammonia which is produced is passed in a cooling chamber in which ammonia is made to absorb in water. It forms liquid ammonia. The unreacted nitrogen and hydrogen, they are recycled back, and the liquid ammonia can be collected. So what are we doing in this case? We can see a flowchart for the Haber's process. This is what is happening. We start with nitrogen and hydrogen and we get liquid ammonia. Let's see the process one by one. So in the first step, we take nitrogen and hydrogen. It is made to pass through compression pump. Now this increases the pressure and so the atoms separate out. Then the nitrogen and hydrogen atoms, they are made to pass through electrically heated catalytic chamber. In this we have iron or molybdenum catalyst that increases the rate of the reaction and forms ammonia molecule. In the next step, this ammonia which is produced is absorbed in water. So we get liquid ammonia. And the unreacted nitrogen and hydrogen atoms, they can be recycled back in this compression pump. So this is how, using the Haber's process, ammonia is industrially prepared. So the reaction taking place is nitrogen reacting with hydrogen to give ammonia. We use the catalyst iron and molybdenum, and it requires a very high temperature of 450 to 500 degrees Celsius and a very high pressure of 200 atmosphere. So this is the Haber's method for the industrial preparation of ammonia.